So joining the Quantum Breakfast, which was organized by Yanis and me, and she joined together with her husband to Waterloo now. And today she will present us a unified framework for the quantum reverse Shannon Theorem. So Zahra, the stage is yours.
Thank you, Christian, and thanks a lot for inviting me to this great workshop. Yes, I'm going to talk about unified approaches to quantum reverse Shannon theorem. This is a joint work with Debbie Leung in IQC Waterloo, also Perimeter. So let's just talk about the background history of this problem. Reverse Shannon theorem was introduced in this paper by Bennett, Shore, Smalling, and Tapial. So this problem, this was introduced as a dual problem to Shannon's capacity problem. So what does Shannon capacity problem says? Like everybody here knows already about that, but let's just review. It says that if we have access to n many uses of a channel, then we can transmit c n many bits of information. Here we assume that n is very large and c is the capacity of a channel. So in a sense, it's like that if we have n access to a given channel, then we can simulate and see many bits of noiseless channel. So then the reverse Shannon theorem is kind of a dual to this problem, meaning that assume that we have and see many uses of a noiseless binary channel, then we can use this binary noiseless channel to simulate a noisy channel, n uses of a noisy channel. So this is called, as the name suggests, reverse Shannon theorem. And one of the important points about the reverse Shannon theorem and also the Shannon's capacity problem in this paper is discussed is that apparently all the asymptotic properties of a classical channel can be characterized by this one parameter, which is the capacity of the channel. So, and then quantum reverse Shannon theorem was introduced in this paper, in this seminal paper, apparently, I think, published 2014, and also got an award from IEEE for the authors. So, the quantum reverse Shannon theorem is kind of the quantum generalization, and it says that if we have NQE, which stands for the entanglement assisted capacity, if we have this many uses of a noiseless qubit channel, then we can simulate any use of a quantum noisy channel. And one of the key points discussed in this paper is that apparently when we have the classical theory, everything happens in the presence of free shared randomness. We can mimic everything to quantum theory, but here in the quantum theory, we have to access to free entanglement. So in the classical theory, Cn, which stands for the capacity, determines all the asymptotic properties. In the quantum theory, the entanglement assisted capacity determines all the asymptotic properties. So let's talk about more details about what is the task of reverse Shannon theorem. We want to simulate a channel, meaning that if we have an input, we want to construct an output. The output is constructed by applying a channel on one part of the system A, and the other part nothing is done on that, and it kind of acts like a reference system. In classical theory, the input that we have is just fully classical system. Both system A and system R, which is the reference, they are just classical information. In quantum information, or in the paper that I already introduced, we have a pure state shared between the system A and the reference, and we want to do the simulation on this specific input state. So this here is kind of describes the classical reverse Shannon theorem. We have this many access to this source, which is a fully classical state, and then we give the AN system to the encoder or Alice, and then the encoding is done on this input, and then we use a noiseless classical channel to send the information, and then there is the decoder, and the aim of the whole process, assuming that the encoder and decoder share free randomness, is that to construct this specific state that is already defined by applying this channel. And yes, in the classical case of the reverse Shannon theorem, there is this specific structure. We have this rho AR of this specific form. In the quantum case, we have exactly the same situation, exactly the same encoding, decoding. The difference is that the input is of this specific pure state form, and also like we should also change the noiseless classical channel to noiseless quantum channel. And instead of shared randomness, we have shared entanglement. This is actually the dual to the classical case. In this problem, reverse Shannon theorem problem, there are many different variants. For example, one of them is the passive feedback, the coherent feedback, and all these kind of different variations of the problem. Passive feedback, what does it mean is that in the classical case, the encoder gets to have a copy of the output. And of course, this is not possible in the quantum case because we cannot copy quantum information because of no cloning theorem. And also there is another notion that they introduce in the quantum case, and that is coherent feedback. What is coherent feedback? Imagine that we have this channel and consider its isometric extension from A and G. Here is the environment system. In the coherent feedback scenario of reverse Shannon theorem, the encoder wants to retain this G system. They don't want this G system to escape to the environment. They want to keep this G system. We want to keep and unify all these kind of different notions, but of course, because we are working with quantum information, we cannot talk about passive feedback. So we want to talk about the coherent feedback. And our model is very general. We want Alice, the encoder, retain a general quantum system, which we call it K. And if K system is just nothing, a trivial system, then we can say that our model is just a non-feedback simulation. And if we say that K is equal to the whole environment system, we can say that our model completely covers the coherent feedback simulation. So this is the table from the paper, the quantum version. And this, as you see, there are many different variations. We have this classical theorem, then we have the quantum theorem, and then we have this feedback regime, non-feedback regime. And in each of these different setups, we see that different kind of functionals, information functionals determine the rate of simulation. So our aim was actually to simplify the whole situation a little bit and introduce a unified model that keeps, like, not all of them not possible, but some of them under the same flag. So how we want to do that? Assume that we want to simulate a channel, but then this state, I said that in the classical case, both system A and R classical. In the quantum case, this is just a pure state. We assume that this is a general mixed state. It can be anything. It can be pure. It can be like fully classical, and also it can be anything in the middle. And then we want to simulate this channel, and we want the encoder to retain this K system. So as I explained in the non-feedback case of quantum reverse Shannon theorem, this K is just a trivial system, and in the feedback case of reverse Shannon theorem, this K system is just the whole environment. So when we say that we want to keep an arbitrary system K here, we get to determine which system we want to preserve. So it could be anything. So this is just the general notion. Our setup is just very similar to the quantum reverse Shannon theorem setup. But as I said, we want to have this side information system to be retained or preserved by the encoder. And also we assume that there is free entanglement shared between encoder and decoder. So we had all these different functionals, like, for example, mutual information, or some functionals in terms of entanglement of purification that determine the rate. But here we say that we only have two functionals. So the functional A, which is a function of the channel that I dropped because the channel is everywhere. This is a function of the input, and also error, which gamma is error here. This is A, which stands for assisted case, and there is also one other functional U, which stands for unassisted case. So these functionals are defined here. They might seem a bit complicated, but in the end, they are just very intuitive. You wanna like apply a channel on the input, and this is our prime here is the purification of the whole input system in such a way that the output is almost close to the state that you want to simulate. And then you want to get the infimum over all such CPTP maps. Similarly, for the unassisted functional, we apply CPTP maps here and also do another CPTP map on the environment system such that we get a state here which is gamma close to the state that we want to simulate. And these two functionals basically gives us all possible rates that we can obtain in different regimes with feedback, with no feedback, classical, fully quantum, and all other cases. So one maybe useful point is that the way that these functions are defined, because they are defined on some compact set, and also because of concavity of this for Neumann entropy, we can conclude that the infimums that we had, they are all minimum, and actually we can attain it. This is very useful because in the end we want to construct protocols that can achieve these rates. So for the first functional that is the governing function in the regime of entanglement assisted case, it is actually a very nice function. I draw it here for a given state. It's a function of this gamma error. As you can see, it's a convex function. It is non-increasing. At the point 0, it is continuous for all gamma bigger than or equal to 0. And also it is super additive, which is a very nice property that we will use to singularize the rate. So, for example, when we do the converse analysis, we show that like we get this functional as the lower bound together with some vanishing terms, and these functionals, because we have this sub-additivity, we get to singularize the rate, and this is a nice property because then we can singularize and analyze the rate. And maybe another useful property here was the continuity of this function at gamma bigger than 0, at equal to 0 from right. And when in the end, when we want to define and find the optimal rate, we have to take the limit of epsilon going to 0, which is the error of the simulation. And then we can show that this is continuous. And basically, the lower bound for the rate is the value of the function at gamma equal to 0. Okay, so for the simulation of a channel, when we have access to free entanglement, we show that this functional, the A function with gamma equal to 0 is the optimal rate for the simulation of a given channel. And this function is actually computable. It is single letter and it has very nice properties. Maybe like I already introduced the function. This might look complicated in some different scenarios, but for example, assume that the input was a pure state between A and R. In this case, the functional is just simply the half of the mutual information between system B and R. Another nice instance is when we have a fully mixed state, but the channel we want to simulate is the identity channel. In this case, we can show that the A function is equal to this difference of two von Neumann entropies, and these are C and Q are coming from Quashimoto decomposition. I didn't want to talk about that because of the time, and we were instructed to talk only 2/3 of our time. Then if you have any question about these two subsystems, I can explain about them later. Okay, this example that I said, like when we have a fully mixed state and we want to simulate the channel, the identity channel is actually was studied by myself and Andreas Winter, and we did this specific problem which was called compression of a general mixed state. So as you can see, we can retrieve this special case with our functional when the channel that we want to simulate is an identity channel, and this when the channel is the identity channel we want to simulate, this problem is just simply a compression problem, because it's like we have a source and we want to like compress it and send it to the decoder, and we want to build the source like almost perfectly, and this is just a very simple case when the simulating the channel that we want to simulate is an identity channel. Okay, so I talked about the entanglement assisted reverse Shannon theorem. Everything was like given by this functional a at point 0 for gamma equal to 0. But when we don't have access to any entanglement, then everything becomes very, very complicated. First of all, then everything, all the rates that we are obtaining, also this is the rate governing all the previous situations that I explained, is the U function with error gamma. But this U function, unlike this A function, doesn't have that nice properties. First of all, let's imagine this simple case when the input is pure and gamma, the error is equal to 0. In this case, the function is equal to entanglement of purification. Entanglement of purification is just an entanglement measure. It's very complicated measure. It's actually, so far, it's not known to be additive or not. So this is very problematic, because if we have two copies of the source, then we don't know whether this is equal to the sum of the two entanglement of purification for two subsystems. So because of this difficulty in analyzing this functional U, in general, we don't get to retrieve all nice properties and a single theorem. What we show is that if we don't have access to any entanglement, then the rate that we can achieve is this regularized formula. So we have this limit of m going to infinity, and then this is the source that we input to the channel, and this is the gamma, the error that has to scale like this. And then we also show that there is a converse bound, and the converse bound is of this form. It is very similar to the like the achievability case, but here we have two limits. Like here, the gamma is not specifically converging to 0 with this rate, but it could be anything. So in general, because this functional is not subadditive and we cannot show if it is like a single letter, these two limits could be different, but we haven't any examples so far showing that these two limits are different or whatever. But as I said, this is not single letter. We cannot compute it, and then we cannot even comment how different these two limits could be. But there are some certain examples that we can simplify and at least say something about the rate. So one of them is when the input is fully classical. So imagine that A system is classical, the reference system is classical. We show that this limit that I defined for the converse, this is the limit for the achievability, both of these limits is equal to this functional, and the gamma here is just 0, the error is 0, and this is equal to entanglement of purification. This is one case. The other one is when the input state is pure state shared between A and the reference. Also in this case, we show that the lower bound and the upper bound, they match. They are both equal to this quantity, the U function at gamma equal to 0, and they are both equal to entanglement of purification. And so here, like we also retrieve the unassisted capacitive region that they introduced in Bennett et al. Paper. But there they assume that K is just a trivial system, but we obtain this result for general case system. So maybe one more example when we can analyze this functional, and this example is actually when we want to simulate an identity channel. Assume that the channel n that we wanted to simulate is this equal to this identity from A to A. In this case, also the lower bound, the upper bound, they match. They equal to this functional. It is still an kind of multi-letter, but we can show that actually we can single letterize and show that it is equal to von Neumann entropy of the two subsystems in Quasimodo decomposition. So in a sense, when we are doing this simpler simulation of an identity, channel, we can single letterize, and this is actually another result that we retrieve with this U functional. This is the general mixed state compression that I had done with Andreas Winter, and this is the governing rate. So maybe I can say just a little bit about the code construction, because I don't want to explain something that can be too complicated for the presentation, but some very general ideas. What we do is that we use already known protocols for compressing and simulating state. Actually, reverse Shannon theorem, as I explained, can be considered like a data compression. You can do everything locally. You can simulate the channel locally and then try to compress and send the information. So what we are doing is exactly like that. We apply all these functionals that we obtain, like these isometries that we obtain in the optimizations of the definition of the U and A function, and then we apply them locally. And then once you apply them locally, we have this local system B and E, and when we try to use Schumacher compression to send this information, and we can show that the rate is equal to this functional, for example, this U functional here. And the error is bounded like this. And when M goes to infinity, the error also goes to 0. It's like a block coding. Like, for example, in the channel capacity, we know that the rate is coherent information, but the coherent information is not single letterizable. So what we do is that we take block of information and we code them, and we in the limit of the length of the block going to infinity, we obtain the rate. It's kind of similar situation here. And because the block length, this M, also appears in the error, we have to make sure that when we take many copies of the state, the K scales in such a way that the error goes to 0. And okay, maybe I give a summary of what we have done. Is that we unified classical and quantum reverse Shannon theorem, and also we brought to the picture all other possible scenarios that neither classical nor quantum reverse Shannon theorem covered, and it was the case that we had all these general mixed states as the input. And it could be that when we want to simulate a channel with different inputs, we get all different cases that these two theorems didn't cover. So two resources that we consider was quantum communication and free entanglement between the encoder and the decoder. So one of the things that we can do, it could be the extension, and also this problem is already mentioned as an open problem in the Bennett et al. Paper, is that we consider all different kind of resources: quantum communication, classical communication, entanglement shared between encoder, decoder, and also shared randomness. And then we find all possible trade-offs between these different resources. This is one point that we don't know how to do it yet. And the other important open questions that we left is that we still don't know how to evaluate this functional when we take the limit. So we need to understand the convergence properties of this functional. When gamma is going to 0, if we first take this limit or that limit, and we change the order, if it matters, and if it doesn't matter, how in the end, whether we can single letterize this U functional. So this is related, this U functional, as I said, is more complex, but in special cases just reduces to entanglement of purification, which is known already to be super complex. The other important question or takeaway that I would say is that we want to, in general, understand this U function, or for example, entanglement of purification, if it is additive or not. By additivity, meaning that we want to evaluate, for example, 2 copies of the functional, two copies of a source, and we evaluate the functional for the 2 copy. We want to see whether it is equal to some of the functional for 2 times the functional for a single state. And yeah, that's the message that I wanted to give, and feel free to ask questions.
Okay, thank you. So,
yes, many thanks also from my side. I have one question regarding this K. Probably it's useful to think of this also in the setting that it is a degraded version of what the receiving party gets.
No, it is not actually a degraded version or anything, but it can be anything.
Yeah.
As long as you can define that, you can find a channel that gives you this case system at the output, we can define a reverse Shannon theorem with this case system. So it doesn't matter in the end.
Okay, so there's nothing specific happening if it is degraded.
No, well, maybe we can simplify the rate. If, for example, we can show that K is a degraded version of the output, maybe we can simplify, maybe that's a good example to simplify the U function in some more extreme cases. But in general, no, we don't have any assumptions on the system K.
Okay, thanks.
So what is the norm for the closeness of simulation? It's L1 norm, is it? For the, if I understand correctly, the reverse Shannon theorem is about simulating a noisy channel to a noiseless channel. So
yeah, then there is also, like, it doesn't matter in the end because reverse Shannon theorem is like in the asymptotic regime, when the error converges to zero, whether you consider fidelity here or like trace distance, it doesn't matter because you can translate them.
So, but it's L1. So it's fidelity and trace distance there, but it's L1.
Yeah.
What motivates the use of L1 as a measure of closeness in this scenario? I don't understand this. I mean, I see you can formulate a mathematical problem and try to solve it, but what really motivates the use of L1 here?
So, I mean, the motivation was just you wanna find a measure to say that how much output is close to the input. You have to induce a measure here.
Yeah, but what?
But like maybe I would say one of the nice properties of fidelity or trace distance is that it's contractive when you apply CP-TP maps. Like it's monotone. Like when you apply CP-TP map, it increases fidelity and it decreases the trace distance, right? And this is one of the key properties that we use in like analyzing both the direct part and the converse part. That's one point.
Shall I put a contrary?
Yeah.
So see the L1, I mean the L1 or the trace distance, essentially a linear function in the interval 0 to 1, right?
Yeah.
Probability measures are essentially concentrated in 0, 1, in 0 to 1. So why not induce a concave function to cost the distance? Why use a linear measure? I don't understand this. I mean, a whole of quantum information theory is built on that, but I want to know why.
So maybe another example.
You answered my question, right?
Yeah. One of the reasons is that we use the properties of this like fidelity or trace distance to do like converse analysis, right? And one of the properties that, for example, we use to show that this functional is convex is actually is the concavity of the fidelity. And then because we use the concavity of the fidelity and we obtain that this functional is convex and also decreasing, we can show that this is lower semi-continuous at gamma equal to 0. And because of this property, we can show that the rate that we can obtain in the lower bound is this A, right? When gamma, instead of having gamma going to 0, the lower bound is actually this functional at gamma equal to 0, which is very important because then the lower bound that we're obtaining is like very high compared to lower bound that we could have obtained without taking the limit, you know? And then we can also, I mean, I'm saying that if we didn't assume fidelity or trace distance, maybe we couldn't show that a functional at gamma equal to 0 is the lower bound. We couldn't do that.
Okay, so no quantum problem, quantum communication problem, we have got single letter characterizations. So all the properties are fantastic, no doubt about it. But if what we are getting is not single letterizable, should we not think about changing the problem formulation and taking a closer look at this? I mean, I don't see anywhere we are having a single little characterization. Not a point-to-point channel, not a Q pointed channel, message communication. Huh? Yes, that's the only problem.
And also the assisted case here, the reason why we could say that the function
I
at
want to ask
zero
the question, I mean, just as this is on information theory, I just want to ask the question, okay, should we really stick to this formulation, the L1 distance, okay, through and through it's there, but nowhere it's really giving us the result we want.
Well, I'm not sure,
Huh?
and I don't know if we induce a different measure here, whether we can use like different properties of this measure, maybe say something about the regularization or something. Yeah.
That's exactly what I said. So probability distances are probability measures are concentrated in 0, 1. You're looking at a linear cost function, right? Why should you have a linear cost function? You should have a concave cost function, something like log. Why have a linear cost function? I understand that we're getting some results here and there, but we're really not getting all the results we need. So is the formulation really?
But in the end, like fidelity is like concave. It's not linear.
That is true, but just a thought. I understand. I'm not solving the problem, but
And also maybe one other point, at least for the trace distance and fidelity, we can show that in the regime that we want to take the limit of error going to 0, it doesn't matter like which one we take into account. So if we change the measure and if we can show that it still gives us like equivalence when the error converges to 0, then it's not gonna matter either. So as long as it doesn't have this property of being equivalent to fidelity and trace distance in the regime of very small error, it doesn't matter, but I haven't seen any kind of measure that doesn't have this property. Thanks again.